world formed through a series of devastating cataclysms.
It could have literally blown the Earth to bits, and then we wouldn't even have a planet today.
An apocalyptic planetary collision. Millions of brutal cosmic strikes. And the most powerful blast in the universe, a supernova.
Our atoms would have been scattered into outer space.
Yet these catastrophes created the planet we know today.
The Earth is an incredibly special place. It seems like everything has worked out just perfectly.
Could other planets have formed the same way? If so, the universe could be full of Earths and full of life. Our planet is extraordinary. It provides everything life needs. Trillions of creatures, plants, and us.
Well, you look down at the Earth from space, and everything that we know of that's life is down there on that planet, that beautiful planet that you now are going around every hour and a half. And that's almost overwhelming, just the beauty of the Earth.
It's unique in our solar system, but is it unique in the universe?
It's important for us to understand the conditions that led to the formation of the Earth, because then we can look for those conditions around other stars, and if we find those conditions there, then that would suggest that other Earths could be forming elsewhere in the universe.
Could there be other planets like ours among the stars? To find out, we must travel back in time and discover how the Earth was made. Rewind the clock 4.5 billion years, and this is what you see. This speck of dust will become the Earth. By combining with countless others. They're all part of a giant cloud called a stellar nursery. The first step of planetary formation is about to start. An event that will transform the cloud into thousands of infant solar systems, including our own. The same process is happening today, 7,000 light years away, in the Eagle Nebula. Our own solar system formed inside clouds of gas and dust like these.
There are these three trunks of gas, and they're nicknamed the pillars of creation. And they're trillions of miles long. These are huge structures.
The clouds look dense, but they're actually very sparse.
These gas clouds are incredibly tenuous. You'd have to compress basically a mountain's volume worth of this stuff, squeeze it down just to make a little tiny rock like this.
To compress the gas and dust into dense stars and planets takes a supremely powerful event. One that can only follow the death of a giant star. In 2007, the Spitzer Space Telescope captured this image. A ball of hot gas behind the Eagle Nebula. Evidence that a huge star has exploded and sent a vast wall of gas racing toward the pillars.
there's a wave of hot material approaching the pillars of creation, and this may be a shock wave from a supernova, a dying star.
Supernovas briefly outshine entire galaxies. Superheated plasma blasts into space at 70 million miles per hour. A mighty shock wave speeds toward the pillars of creation. When it hits, it will demolish them. It will also create new worlds. Supernova shock waves smash into the pillars, compressing the thin gas and dust into dense clumps. Each is a new star, a new solar system.
Molecular cloud minding its own business gets blasted by a supernova explosion, crushing the cloud down into stars and planets.
Wind back 4.5 billion years, and our solar system starts the same way. A supernova crushes a massive, dusty cloud into a protoplanetary disk. A thin, nebulous cloud becomes a dense whirlpool of gas and dust. A solar system in the making. One star is destroyed, a new star is born. Our sun and its planets. This is the first link in the long and unlikely chain of events that made our world. For Earth to even be here, we had to beat astronomical odds.
A host of different factors have to line up to get a planet just like the Earth. You have to have the right distance, the right size, the right kind of moon.
On Earth, all the conditions are just right for life.
To get a world like ours, you need a lot of aces. Somehow, our solar system hit the jackpot. But the big question is, did it happen anywhere else?
One of the universe's most violent events triggered the birth of our planet. A sparse cloud crushed into a dense swirl of dust. Some of this dust will become planet Earth. But how do tiny dust grains create entire worlds? A supernova explosion triggers a chain of events that will eventually create the Earth. The formation of our solar system. A hot ball of gas grows in the center. This will become our sun. The dust that swirls around it will form the planets. But first, the grains must stick together.
So we have this interesting conundrum, right? So this disk consists of gas and dust particles. They're about the size of, let's say, particles in smoke, right? Let's say cigarette smoke, right? So these are small things. And somehow we have to get from those little grains to what we see on the Earth.
Gravity is a powerful attractive force. It shapes galaxies and solar systems. But specks of dust are far too small to pull on each other. Somehow, they clump together to form planets. So if gravity doesn't bind them, what does? In Germany, scientists are on the case.
Okay.
They can simulate how dust behaves in space inside a huge tower.
Here we do free fall experiments. So the whole experimental setup, including our dust aggregates, are in perfect free fall. It is simulation of space, but a very good one indeed. I think this is the closest you can get to space on Earth.
Researchers placed dust in a container and load it into a launch capsule. At the base of the tower, they lower it into a super powerful catapult. This launches the half-ton capsule from 0 to over 100 miles per hour in a quarter of a second. 400 feet up, the capsule reaches the top of the tower, then plunges back down. A drum of polystyrene balls 30 feet deep breaks its fall. All this gives just 10 seconds of zero gravity. Just enough time, they hope, for the dust to stick.
3, 2, 1, and go.
Moments after the capsule launches, the dust inside becomes weightless. The grains clump together, just like the early solar system. These images reveal how dust particles came together 4.5 billion years ago to form the Earth.
The force that binds the aggregates together is not gravity. They are too small for gravity to be efficient. We think the force that binds the aggregates together is electrostatic force.
It's the same reason that when you pull your clothes out of the dryer, you know how the clothes sometimes stick to you? That's the same effect that allows one dust particle to stick to another.
Dust particles join to form balls of fluff.
The little static charges that they have can make them stick when they hit. And you get something sort of like the dust bunnies that I have a lot of underneath my bed.
These cosmic dust bunnies are planets in the making. They start out smaller than a pinhead, then grow. The dust is now in clumps, but it's still just balls of dust. Turning dust balls into rocks takes a whole new process. A cosmic electric storm. Space clouds build up charge just like clouds here on Earth, generating huge bolts of lightning.
Balls of dust can turn into solid rocks by an energetic event like lightning.
The electric bolts smash through the dust balls and heat them to 3,000 degrees Fahrenheit. In minutes, they cool and fuse into solid rock. Meteorites today still carry these ancient rock balls inside them. These tiny globules were once the building blocks of planets. To form the Earth, these tiny balls must collide, stick, and grow.
Rocks begin to build up by accidental collisions, which can take a long time.
Eventually, the protoplanets, as we call them, the baby planets, get the size of asteroids, kilometers across.
The baby Earth is now the size of a few city blocks, big enough for a new force to take charge: gravity.
At that point, a single asteroid will gravitationally attract a neighboring asteroid. And so those two asteroids that would have passed in the night are gravitationally attracted and they hit each other.
Once gravity starts to rear its head, things really speed up because instead of just randomly plowing through material and getting bigger that way, now it's starting to draw material in.
Gravity pulls rocks together, then holds them there to produce bigger and bigger piles of rubble.
So this formation process, which was taking a long time to get to the size where gravity kicks in, suddenly gets kicked into overdrive, and the planet grows very rapidly.
But planets are more than just overgrown rock piles. These rocks are lumpy and inert. How did the Earth become round and full of life? The early solar system is a construction site for planets. Dust sticks together to form rocks. Rocks join to form asteroids. But most asteroids look nothing like Earth.
And when you look at a close-up of an asteroid, it looks like some kind of distorted peanut, like a potato that's been sort of bashed. You can see giant craters and oblong shapes.
The young Earth is one of billions of misshapen space boulders. To become a planet, it must first become round. That process only starts when it's several hundred miles across, when its own internal gravity begins to change its shape.
Once you get enough material, enough mass, the gravitational force becomes stronger. Any giant mountain will be crushed down by the force of gravity.
The gravity is so strong that can actually break rocks, and the rocks itself can act like a fluid, making an object round.
Huge outcrops of rock crumble and fall. The immense self-gravity of the early Earth crushes it into the most efficient shape. A vast round ball of rock. A lopsided pile of rubble transformed into a miniature world. The Earth has a new shape, but it's still just a ball of rock. Its structure will also soon change. Cosmic rocks and boulders still rain down from space. Each collision heats the ground.
There's a huge amount of energy stored in an object that's moving rapidly, and when that hits the Earth, all that energy is dumped into the material, and that heats it up and melts it. And the Earth became molten and stayed that way for a long time.
The young planet is no longer solid rock. It's a seething, molten mass. Just like this blast furnace at the Severstall plant in Detroit.
Believe it or not, this process behind me makes life on Earth possible.
They feed in ground up iron ore, a mixture of rock and metal. Just like the early Earth. Put iron ore in a furnace, and the heat melts everything.
This molten iron is at 2,700 degrees Fahrenheit. That's about the temperature of the surface of the Earth 4.5 billion years ago. Imagine an entire planet molten. In the distance, you will see thundering volcanoes spewing out lava. It would be a scene right out of Dante's Inferno.
Iron is heavier than rock. Now molten, they separate.
This is amazing. We're witnessing a process which created the very crust of the Earth billions of years ago, the crust that we walk on every day.
Molten rock rises to the surface and cools to form the crust. molten iron sinks underneath. Inside the Earth, it sank all the way to the planet's core. The rocky surface is where we live. But without Earth's molten iron core, none of us could survive.
This process separated the iron from the rocky minerals. As the iron descended to the center of the Earth, it eventually created a magnetic field, and that's why we're here today.
The molten iron swirls inside the Earth's core and generates a powerful magnetic field around the planet. A cosmic shield against deadly radiation from space. But the young Earth is still small, far smaller than the Moon today. This newly formed world must grow. It must also avoid being blown to pieces. Thousands of protoplanets are hurtling around the solar system, and some are heading straight for Earth. It's 100,000 years since our solar system formed. The young Earth already looks like a planet. It's round. It has an iron core and a rocky surface. Yet our baby planet is just a few hundred miles across. It has a long way to go. It must grow 4,000 times more massive. And it has competition. Thousands of other protoplanets shoot through the solar system, often colliding at over 20,000 miles per hour. You can find proof of this ancient destructive era in modern-day Arizona. Not Meteor Crater itself, that's just 50,000 years old, but the asteroid that gouged it out. That was 4.5 billion years old. Mark Sykes and Marvin Kilgore think the asteroid came from a violent event in the early solar system. The asteroid flew through space for billions of years. Then it hit Earth. They aimed to find a fragment of the asteroid, a remnant from the period of planetary formation.
About 6 miles from here is Meteor Crater, and that was an impact 50,000 years or so ago, and it spewed a bunch of pieces out.
They're convinced the original asteroid was rich in iron, so they've come prepared with some impressive metal detectors.
Does it work?
Oh, yeah.
That's the sound we're listening for.
But even with a quad-drawn metal detector, meteorites are hard to find.
Yeah, are you pretty convinced there's nothing there?
Yeah, I don't really, not detecting anything.
They find metal, but no meteorites.
My great discovery of the afternoon has been this bolt and this piece of wire.
It takes hours of searching and many false alarms. Then, with the light fading, the detector sounds again.
How about that? Success at last.
This meteorite is over 90% iron and nickel. it could only form right in the core of a protoplanet. The protoplanet it came from must have smashed apart in a brutal collision.
Well, in the early solar system, it was a pretty violent place, and these protoplanetary embryos would smash into each other and they would shatter each other, exposing the interior cores like this. It was a very tumultuous time.
Entire worlds reduced to chunks of rock and metal and scattered into outer space. In the early solar system, these vast collisions are common. The young Earth is in danger. The period's name is the Titanomachian, literally, the War of the Titans. All rocky planets, the Earth included, go through this destructive phase. Sometimes they shatter completely. Sometimes one consumes the other.
All the big guys are sort of competing with one another in a very violent way, actually, to see who comes out on top by eating all their neighbors.
The battle lasts over 30 million years. Finally, thousands of protoplanets have combined into a few full-size planets. Mercury, Venus, Earth, Mars, and a fifth planet, Theia. It's racing toward Earth, our planet's last giant impact. Theia is the size of Mars, big enough to destroy the Earth.
If that thing had hit us straight on, it could have literally blown the Earth to bits, and then we wouldn't even have a planet today.
If this Mars-like object had a direct hit with the Earth, perhaps there would have been another asteroid belt where the Earth is today.
But Earth is in luck. Instead of a head-on crash, Theia strikes a glancing blow. It's the most violent event the Earth has ever known. The impact turns the Earth back to a molten world. A vast magma ocean 600 miles deep. The Earth barely survives. And the encounter changes our world forever. Material blasts out into space. Enough rock to build a mountain as wide as America and 10,000 miles high.
It would have been so much energy, so much catastrophe. Huge amounts of material blasted off and went into orbit around the Earth.
The debris forms a huge ring around the Earth. This gathers together to form two rocky bodies, both orbiting the Earth.
Something the size of Mars hit the Earth about 4 billion years ago. Lots of material would have been thrown off. We now think that it may have formed not only one moon, but two.
For millions of years, two moons dominate the Earth's sky. Eventually, they drift together and collide. Two moons merge into one. The massive moon we see today.
There's no other planet that we know of that has a moon as large as ours in comparison to the size of the planet. We're almost a binary planet, two worlds going around each other.
Without this large moon, we might not even be here.
The moon plays a key role in the survival of life here on the Earth. And the reason is that the moon in its orbit stabilizes the Earth.
The moon keeps the Earth spinning at the same angle. That steadies our climate.
The fact that the Earth's axis stays in the same direction as it goes around the sun produces the seasons, but regular seasons, things that life can depend upon as it evolves.
Earth is neither too hot nor too cold for life, thanks to our distance from the sun and our massive moon. The Earth is not covered in ice or steam, but in liquid water. Yet that water must come from somewhere. The newly formed Earth is dry. To get water, our planet must once again face disaster. It's 500 million years since the sun first ignited. 4 billion years from now, the first humans will set foot on Earth. The moon has just formed, and the Earth is a desert.
One of the more amazing ideas in astronomy is that the Earth started out hot and dry. There was no water here originally.
As the planets formed, the sun's intense radiation vaporized the water in the inner solar system. Farther from the sun, temperatures were cooler. So in the outer solar system, ice and water collected on comets and asteroids. While closer to the sun, the young Earth was dry.
So things changed. What happened? How is it that now we have this wonderful water cycle? Well, the water probably came from somewhere else.
If you want to have a solar system that has a lot of water in it, you have to bring it from the outer parts down into the inner parts. And you can do that through comets and asteroids.
Comets and icy asteroids contain huge reserves of water. But they're hundreds of millions of miles from the young Earth. Then, something changes. An event that tosses the asteroids and comets right across the solar system. Jupiter, Saturn, Neptune, Uranus take a cosmic roller coaster ride.
So this isn't an event that happened when the solar system was young. Think of it as more of its teenage breakout years where they just started to party for a while.
The young planets have not yet settled into stable orbits. As their orbits shift, Jupiter and Saturn fall into an intricate dance. Every time Saturn orbits the Sun once, Jupiter orbits twice. So they always line up at the same spot. Each time, gravity tugs them in the same direction. First, they destabilize each other, and then the entire solar system.
The whole thing just goes kaplooey. The analogy I like to use is when a bowling ball hits pins, it just goes bam all over the place. That's what this would have looked like.
Planetary pandemonium. Neptune and Uranus switch places. Saturn races outwards. The giant planets scatter billions of asteroids and comets onto new paths. Many head for Earth.
These asteroids and comets would have been scattered all over the place, right? Some of them hitting the Earth and Moon.
Cosmic missiles bombard the Earth.
We believe that every square inch of the Earth got hit by a comet or an asteroid, during this period. It would not have been a fun time to be here.
The bombardment lasts hundreds of millions of years. Until finally, the gas planets settle into the stable orbits we see today, restoring order. But Earth itself has fundamentally changed. Those comets and asteroids were not just made of rock, but of ice, frozen water.
Comets, we know, are made out of ice. They're dirty snowballs in outer space, and even asteroids can bring water and ice to the Earth.
Our oceans are full, thanks to the cosmic hailstorm.
So, next time you're drinking a glass of water, realize that you're probably drinking comet and asteroid juice.
The arrival of water is the final step to create a habitable planet. A sequence of catastrophes has created a world that's perfect for life. But has it happened elsewhere among the stars? Or are we alone? How did we get here? Planet Earth only exists because of a chain of extraordinary events. A lucky throw of cosmic dice.
5 billion years ago, the odds would have seemed extremely slim that a planet like Earth would form in a rather unremarkable arm in the Milky Way galaxy. It's like trying to throw 2 sixes, but with dice that have thousands of sides.
We know it happened once, else we wouldn't be here. But what are the odds it happened elsewhere? That other planets have life. Life like ours needs a planet with the right temperature and size, a stabilizing moon, a protective magnetic field, and just the right amount of water. The conditions must be perfect. Yet amazingly, there may be countless Earth-like planets out there waiting to be found. Thanks to the sheer scale of the universe. We may find one any day now with the Kepler Space Telescope. Jeff Marcy is mission co-investigator.
It has only one goal, and that's to discover Earth-sized planets around other stars that you see in the night sky.
Earth-sized planets are hard to spot. Before Kepler, astronomers took 20 years to discover around 500 planets. Most were gas giants hundreds of times bigger than Earth. Since Kepler, that number has exploded.
Kepler has already discovered a couple thousand planet candidates. Many of them are members of multi-planet systems, 2, 3, 4, 5, and even 6 planets, all orbiting the same star. So we're finding an absolute avalanche of planets out there among the stars.
Kepler has found one planet only twice the size of Earth and the right temperature for life. We don't know yet if this planet has other Earth-like attributes, like liquid water. But even if it doesn't, there are many more planets out there. Kepler has found only a tiny fraction of them because it only looks at a small part of the sky.
It's not even looking at the whole sky. It's looking at a very tiny slice of stars in the galaxy. And in fact, if you were to look up, you could cover it with just your thumb.
In the whole of our galaxy, there are 200 billion stars. Many will have planets.
Based on our knowledge from Kepler and other searches, something like half of those stars, perhaps even more, harbor planets.
That means at least 100 billion planets have formed in the Milky Way. Earth-like worlds may be rare, but it seems a safe bet they're out there somewhere.
So the odds of getting an Earth-like planet are extremely small, much smaller than getting a double six at craps. But if you have a lot of dice, you're guaranteed to get sixes.
And if you have a lot of planets, you're guaranteed to get Earths. There are so many planets in our galaxy. Even if the chances are 1 in a million, there should be thousands of Earth-like worlds.
Our universe at large has hundreds of billions of galaxies, each of which is more or less like our Milky Way. So the number of planets in our universe is virtually uncountable.
Alien Earths must be everywhere.
Now, we haven't discovered even one of them yet, but statistically speaking, it is a rock-solid certainty. There are millions of billions of planets like the Earth out there.
And with that many Earth-like planets, surely some of them will have intelligent life.
I would bet everything, I would bet my house, that there is another Earth out there somewhere.
There really can be no doubt that elsewhere in our universe, there are other smart critters who are asking themselves, gee, I wonder if there are any other intelligent species out there in the universe.
The night sky is full of stars, galaxies, planets, and asteroids.
Asteroid actually means star-like. Even in the very best telescopes, they look like nothing more than just points of light in the sky.
They're cosmic boulders, and there are trillions of them. From the size of a car to giants hundreds of miles across. Together, they tell the story of how we came to be. The Earth was made by asteroids. Four and a half billion years ago, the solar system is a vast cosmic whirlpool. Dust sticks together to create asteroids.
In our own solar system and in every solar system, the first objects to form, the first large rocks before planets form, are essentially asteroids.
There are no planets yet. Instead, trillions of rocks and stones swirl around the newly born sun.
It would have been a very strange place, kind of like a merry-go-round of all these objects orbiting around the sun. And there are millions of these asteroids that are just in different sizes and different shapes.
These ancient asteroids will shape the solar system and build the planet we live on.
Asteroids are so much more than just rocks in space. They're the building blocks of our very own planet.
Billions of small asteroids must clump together to make a planet. But asteroids move at thousands of miles per hour. Getting them to stick is hard.
We're here at the stock car race. See what the early solar system may have looked like.
High-speed car collisions cause damage. Parts smash off. Asteroid collisions are the same. To join together, somehow they must collide and stick. Stock cars show how this happens. They move fast, but all in the same direction. Just like the asteroids in the early solar system. When collisions happen, they're relatively gentle. Instead of smashing apart, they join together. These are planets in the making.
They're going around almost at the same speed, and they begin to stick together, and that's how planets begin to form.
Asteroids gather into rock piles, like two cars locked together. As more asteroids collide, the rock piles grow. Building whole planets this way would take billions of years. Yet the planets formed in just a few million years. How? When the rock piles reach mountain size, gravity speeds up the process.
Gravity started to become important when they were about the size of one of the Rocky Mountains, like Pikes Peak behind me. It was when they were several miles across that they had enough mass that their gravity could start to draw material in. Now, if the Earth weren't here, and it were just Pikes Peak over there a few miles away, I would very slowly start to drift toward it, faster and faster, accelerating the whole way, until I actually impacted it. The gravity would draw me in, it would pull on me, until I actually hit the mountain itself.
Large asteroids are mountains in space. The early solar system is full of them. Their gravity pulls other asteroids toward them. The larger an asteroid becomes, the more rocks it pulls in, and the faster it grows.
At that point, the events happened very quickly. It would actually draw that stuff in and grow very rapidly.
One of these early space mountains keeps on growing until there are no rocks left to pull in. It's no longer an asteroid. It's a young planet, the Earth.
All of the planets, even the Earth, they owe their existence to the fact that there were asteroids back then.
This is how all rocky planets form. Asteroids join together until there are no more left. Mercury, Venus, Earth, and Mars are all overgrown asteroids. But beyond Mars, something went wrong. No rocky planets. Instead, billions of rocks and boulders that never join together. The asteroid belt. Out here, construction came to a halt before a rocky planet could form. Because of Jupiter. The gas giant had already formed nearby.
Jupiter is humongous. It's the 800-pound gorilla. It dominates everything gravitationally.
4.5 billion years ago, Jupiter's gravity causes havoc. It flings asteroids in every direction. Giant boulders scatter from their regular orbits onto extreme, chaotic paths. The stock car race ends, and the demolition derby begins.
Once Jupiter got involved, the solar system began to look like a demolition derby. Things colliding with each other, going in all sorts of different directions.
A cosmic pileup. Rocks smash into each other from every direction. Violent, chaotic collisions. These rocks don't clump together. They shatter and create the asteroid belt. Violent collisions still rock the asteroid belt today. In 2010, the Hubble Space Telescope captured this: the aftermath of a hypervelocity collision. asteroids can both create and destroy. If many of them come together gently, you get planets. Too much violence, and you get the asteroid belt. Billions of rocks and boulders, a graveyard for a planet that never formed. The asteroid belt is a mysterious realm, full of danger and full of promise. A new frontier just waiting to be explored. Asteroids are as diverse as planets or moons. Some are metallic, some rocky, some icy. Some even have their own moons. They come in all shapes and sizes. From boulders all the way to miniature worlds. And they're everywhere. Distant solar systems have their own asteroid belts. The star Epsilon Eridani is just 10 light years away. It has not one, but 2 asteroid belts. Another star has a belt 25 times larger than our own.
If you were actually living on a planet in that solar system, the asteroid belt would look like a much brighter than the Milky Way, a big streak across the night sky.
Asteroid belts are the scraps left over after planets have formed. So they tell us a lot about their solar system. Our asteroid belt is full of variety. Millions of strange asteroids, each with a story to tell. Yet we have barely explored it at all. That's about to change. The first mission to the asteroid belt is underway. The Dawn probe. Its goal? To explore a mysterious, distant realm.
We're going to learn more about the main belt asteroids from this one mission than we will have since we've discovered the asteroid belt in the first place.
In July 2011, Dawn arrived at its first target and sent back these pictures. Vesta is the second largest asteroid in the belt. It almost became a planet. Then Jupiter's massive gravity stunted its growth. Today, it's a miniature world.
One of the common misconceptions about the asteroid belt is that things are fairly small. But some of the largest asteroids are really more correctly thought of as minor planets. They're several hundred miles across.
Vesta even has a mountain 3 times higher than Everest. Mark Sykes is co-investigator of the mission.
It's just a real excitement because you're seeing a new world for the first time, and you know just enough to be dangerous in trying to explain what it is that you're seeing.
Vesta is like a snapshot of the infant Earth, when it was just as wide as Arizona.
We're seeing perhaps what an embryonic early terrestrial planet like Earth looked like in the first few million years of its history.
The Dawn probe has already found that Vesta has an iron core like the Earth. Evidence that the Earth's core formed when the planet was still young. This stunted world offers us a window on the Earth's distant past.
We're seeing things that we didn't necessarily expect, but that's what makes it fun.
After Vesta, the Dawn mission will head into the asteroid belt's outer reaches. to explore an icy primeval world, 4 times bigger than Vesta. There, Dawn aims to settle another mystery about the Earth's past. Where did our oceans come from? The asteroid belt is ancient, violent, and remote. Hundreds of millions of miles from Earth. But not all asteroids stay in the asteroid belt. They can roam all over the solar system. The moon's surface records a violent past, a massive cosmic bombardment.
We see evidence every night when the moon comes out. What do we see? A pockmarked, barren world. Evidence that there was an intense rain of asteroids and debris that came from outer space, completely disfiguring the surface of the moon.
Millions of craters cover the moon, including the largest in the solar system, 1,500 miles across. Itself scarred by thousands of smaller craters. A storm of asteroids blasted the moon 4 billion years ago. And if that happened to the moon, it must also have happened to Earth.
The Earth is a much bigger, more massive target in space. For every one of those craters you see on the moon, you've got to imagine 50 or 60 craters here on the planet Earth.
The impacts back then must have been horrendous. Every few weeks, a gigantic object hurtling from outer space, gouging out a huge chunk of the planet Earth.
We call it the Late Heavy Bombardment. For 200 million years, fireballs rain from the sky. The impacts trigger earthquakes bigger than any in recorded history. 10,000-mile-per-hour hurricanes rip through Earth's primitive atmosphere. But asteroids also bring a new substance to Earth. Some asteroids contain ice, frozen water that melts on impact. Each asteroid brings a little more. But could asteroids really bring enough water to cover 2/3 of our planet?
One of the questions we have is, how did water get to the Earth? Because the original Earth, we think, was very hot and very dry.
NASA's Dawn probe aims to find out. The asteroid belt still contains icy asteroids to this day, in the coldest, most distant part. In 2015, Dawn will arrive at the solar system's largest asteroid, Ceres.
Ceres is 1/3 the mass of the entire asteroid belt and 4 times as large as any other known asteroid.
A lot of it looks like pure ice.
Ceres has a rocky interior and ice-rich mantle. It's far enough away from the sun, it's cold enough that it's stable.
Ceres is just 600 miles wide, yet there may be more frozen water here than all the fresh water on Earth. The Dawn mission will find out for sure. If Ceres really does hold so much ice, it could help explain why the Earth has so much water. When asteroids bombarded the Earth 4 billion years ago, massive icy bodies like Ceres could have brought vast amounts of water.
Water itself, in the form of ice, came down from the heavens to create the lush oceans of the Earth.
And not just the oceans. Clouds, rivers, glaciers may all have come from space. The Dawn mission may uncover something even more significant on Ceres. It may find an ocean underneath the ice, an inner mantle of liquid water, melted by heat from the dwarf planet's core. Life as we know it depends on water. Wherever we find water, we may find the spark of life.
If there is a liquid water ocean underneath the surface today, that begs the question of whether there could be life there.
Extraterrestrial life could have started in the asteroid belt. Ceres could be home to basic life forms, flourishing in a subsurface ocean. If asteroids like Ceres can support life, that could reveal how life started on Earth. 4 billion years ago, asteroids bombarded the young Earth. They brought water, and they may have brought life. From the asteroid belt to Earth's new oceans, primitive organisms that thrived and ultimately evolved into all the Earth's creatures. A planet that brims with life. Our earliest ancestors may have arrived from the asteroid belt.
Perhaps these little worlds could be incubators of life throughout our solar system, maybe even in other solar systems around other stars.
Asteroids may bring life to worlds throughout the universe. They may also bring death. Asteroids are crucial to life in the universe. But once life gets started, asteroids can also end it.
Asteroids really have two sides to them. They're sort of creation and destruction all wrapped up together.
Planet Earth is right in the firing line.
We've come to realize in recent years that we live in this kind of a cosmic shooting gallery.
Astronauts witness this firsthand.
When I flew on Apollo 9 and I went outside the spacecraft, it's very likely that I was hit by, a very, very small asteroid. And, it will make a hole in a spacesuit.
Most objects in the Earth's vicinity are tiny, but they move at thousands of miles per hour.
So the suits are very, very well built, the result of which is they're very heavy. But, we've never had one penetrated yet.
The Earth, too, has built-in protection from small asteroids. The atmosphere. When asteroids hit the atmosphere, they burn.
I can remember one night when we were looking down at the dark Earth, and I kept thinking I saw an occasional flash of light, but I wasn't sure. And then suddenly we're realizing, of course, we're looking at shooting stars.
Most people don't realize that on a given night, if you lie in the grass and look up at the night sky, you'll see shooting stars, many of them each hour.
Most shooting stars are the size of grains of sand. These burn up. But larger space rocks can punch right through to the ground. Here's the proof. Meteor crater in Arizona, gouged out by an asteroid just 150 feet across.
You can see the huge force that excavated this, and you can also see the layers of material that were turned over as the crater was excavated. And so some of these rocks around here are kind of upside down from where they started.
There have been millions of impacts like this in Earth's past. There will be more. Imagine a city where Meteor Crater is now.
You'd see a fireball coming through the sky very quickly. You know, this thing is moving at 8 miles a second, and so it wouldn't take very long for it to move across the sky and strike the ground.
Heat from the fireball scorches the surface, but most damage comes after the impact.
Once it strikes the ground, this takes a few seconds to create. So very short time, very large amount of energy, and very devastating effects.
The asteroid is obliterated. A mighty shock wave generates winds 6 times more powerful than a hurricane.
You have the blast that comes out, probably for several miles, and large debris that would crush buildings and homes.
If it hit today, the asteroid from Meteor Crater would be a city killer. But the Meteor Crater asteroid was small. It was likely a fragment from a much larger asteroid.
Whatever it is that hit in Meteor Crater wasn't very big. It was probably 50 yards across, so not even as big as a football field.
There are millions of much larger asteroids. These would cause even more carnage. Country killers, and worse. Asteroids over a half-mile wide could end our civilization. Worldwide killers. We know because it happened already. There are traces everywhere.
There's evidence of giant impacts all over the world, and it's right underneath your feet. And in fact, in some places, it's pretty easy to spot.
Like here in southern Colorado.
So this layer of light-colored rock, that's the KT boundary. And it's called a boundary because it marks the boundary between 2 different time periods. Everything that was put down here underneath the KT boundary had dinosaurs in it. Everything above it, no dinosaurs. So it really marks that point in time when the dinosaurs went away.
The layer is rich in an element called iridium. It's rare on the Earth's surface, but common in asteroids.
So if a giant asteroid came in, smacked into the Earth, blew out dust everywhere, the iridium inside the asteroid would have settled down into a layer all over the Earth. And that's exactly what we see right here.
The clear fingerprint of an asteroid.
There must have been some perfect morning before the asteroid impact when the land of the dinosaurs was still very much as it had been for millions of years. Then there would be something sighted up in the sky, something very bright, very hot.
The asteroid is 6 miles long, big enough to devastate the planet.
The asteroid that came in and formed this layer here was very massive and was moving very fast. And so when it impacted the Earth, that energy was turned into boom, very, very big boom.
It has the force of 5 billion Hiroshima bombs. Large pieces of Earth blow out into space, then rain back down, a storm of fireballs. Wildfires rage across the globe.
In the KT boundary layer is a layer of soot. And that's an indication that there were global fires, that everything on Earth was basically on fire after this happened.
The Earth plunges into darkness. An impact winter. Mass extinction.
Basically, you can think of this as every environmental catastrophe all happening at the same time. It was an incredibly bad day for planet Earth.
A chilling reminder of the threat from space. Asteroids this big will hit us again.
We will go the way of the dinosaurs. We will be survived, most likely by the bugs, the cockroaches. They will be the ones who will inherit this Earth. But hopefully, that's going to be a long time from now.
Is mankind doomed? Or can we dodge fate? Asteroids built our world. They brought water. They killed the dinosaurs and made room for new species. But asteroids are also a threat.
We know absolutely for certain that there will be large impacts in the future. So it's not a question of if, it's only a question of when.
Large meteor impacts happen once every 60 to 100 million years. We're due for one soon, perhaps.
If we want to survive, we need to prepare. We must find the asteroids, determine if they're heading for Earth, then stop them. That's not easy, but it may be possible.
Happily, there's a difference between us and dinosaurs. We have telescopes, and we can get advance notice of an impact.
Asteroids are much smaller than stars and planets. It's hard to see them coming. To track asteroids, you need a giant telescope. Like the Arecibo Observatory in Puerto Rico.
Right now, I'm on top of the largest telescope in the world, and this place may actually be our best defense against getting hit by one of these near-Earth asteroids.
The vast bowl is 1,000 feet across. And it's not only the world's biggest telescope, it's also the world's biggest radar dish.
When you think about using radar to keep track of all the airplanes that are up in the sky, well, this one is so powerful, it can actually track near-Earth objects millions of miles away.
Unlike a telescope, radar can directly measure an object's distance and reveal exactly where it is. That's perfect for tracking asteroids. In 2004, astronomers spot a stadium-sized asteroid heading toward Earth. Its name, Apophis, after the Egyptian god of destruction. The day it might hit us, April 13th, 2029. Friday the 13th.
Apophis was the first near-Earth object of the modern era that had astronomers honestly scared. There seemed to be a 1 in 30 chance of something catastrophic happening.
Arecibo springs into action against the biggest threat from space ever detected. Apophis could devastate entire countries. But the asteroid's path is still uncertain. It might hit, or it might just miss. Only Arecibo can tell us for sure.
The Arecibo telescope was able to reduce the uncertainty of Apophis by 98%. It told us that there was no chance this thing would hit us in 2029.
It will be close. Apophis will pass closer to the Earth than the Moon. Closer even than some communications satellites. We have powerful tools to detect asteroids. Someday, we'll find one that will hit the Earth. How can we protect ourselves? The obvious strategy is to destroy the asteroid before it destroys us. But that could be risky.
You don't want to blow it up because you may end up breaking it into 2 or 3 or 5 pieces, which then end up hitting all around the Earth and wiping out many, many people.
Exploding an asteroid could cause more harm than good. Better to make it miss completely. When an asteroid is headed for Earth, their future paths cross. And they'll both reach that point at the same time. Imagine the Earth is a freight train, and the asteroid is a car, both heading for a railroad crossing. If they reach that crossing at the same time, they will collide. The best way to avoid the impact is not to swerve away from the train. It's to hit the gas or the brakes.
If you can cross the tracks before the train gets there, or wait for the train to pass and then cross them, that's what we want to do with asteroids, just to make sure that the asteroid and the Earth aren't at the same place at the same time.
By simply slowing down the car, we're going to miss. That's the way to avert a collision.
But asteroids don't come with brakes. We need another way to change their speed. One approach is to use the asteroid's gravity.
For a small enough asteroid, all you need to do is park a large spacecraft next to the asteroid.
A spaceship would hover above the asteroid's surface.
You can thrust with your spacecraft to keep it from falling onto the surface of the asteroid. And so it's like a little gravity tractor, using gravity as the tow line to move the asteroid out of the way.
Over time, the gravity between them would slow down the asteroid just enough for it to miss the Earth. Asteroids could shape our future in another way. We could turn them from a deadly threat into a precious resource. Asteroids are a creative force. They build planets. They bring water. But they're also destructive.
Asteroids are both a boon and a threat. Early on, they bring the materials for life. Later on, they can destroy life.
Asteroids bring violence and death. But life may not always be in danger.
Ultimately, if life becomes intelligent enough, it can send objects out to deflect or destroy the impending asteroids.
We now have the technology to divert asteroids. That means we can treat them not as a threat, but an opportunity. We could mine them.
Many of them are just ripe for the taking in these wonderful mineral resources. And so the asteroids in some ways are literally gold mines in the sky.
They're not just gold mines. They're zinc mines, aluminum mines, platinum mines. Just one average-sized asteroid could contain minerals worth thousands of billions of dollars. But first, we have to reach the asteroids. On April 15, 2010, President Obama announced a new plan.
By 2025,
We expect new spacecraft designed for long journeys to allow us to begin the first ever crewed missions beyond the moon into deep space. We'll start by sending astronauts to an asteroid for the first time in history.
Ironically, the easiest asteroids to reach are the same ones that threaten the Earth. As they pass by, a spaceship could rendezvous with the asteroid. Yet even when asteroids come so close, asteroid mining may be too good to be true.
The reason why we're not mining the asteroid belt today and letting the space program pay for itself is because of cost. It takes an enormous amount of rocket fuel and expertise to bring back an asteroid from outer space.
But perhaps we don't need to bring the minerals back to Earth. We could use the resources of asteroids to build settlements out in space.
You don't have to build a space station, it's already there. You don't need shielding because you can simply drill right into the soil and use the rocky material as shielding against radiation and micrometeorites. So in some sense, think of an asteroid as a ready-made space station.
Low gravity makes it easy to come and go. There's plenty of water and all the construction materials that colonizers could ever need.
So one day when we have colonies in the asteroid belt and we need to build cities there, that's where we're going to find valuable deposits of metals in the asteroid belt itself.
A vast band of cities in space, strung across 1 billion miles. And not just cities, but factories to turn metal from the asteroids into spaceships.
Perhaps asteroids could actually provide the metal, the real structure to build our spacecraft. So somewhere up there between Mars and Jupiter, there may be the makings of our future spaceships.
Ultimately, asteroids may be a stepping stone by which we can one day leave the entire solar system.
Asteroids made the Earth. Perhaps they even brought life here. And in the future, asteroids could help humans escape the Earth and colonize the galaxy.
So in a way, asteroids are drawing us out into space, whether to protect ourselves or to expand where we live.
This is our solar system. 8 planets, more than 150 moons, billions of space rocks, dust and gas, all orbit a single star in a giant whirling disk 10 billion miles across. It's been this way for 4 billion years. Everything moves round in an orderly fashion, serene and stable. But our solar system is unusual. Elsewhere in our universe, orbits are nothing like this. They're unstable, chaotic, even destructive.
Even in the nearby universe, we see incredibly violent examples of orbits. Giant planets that hurtle in toward their stars. We see shock waves of thousands of degrees perpetuate through the atmosphere.
There are planets that dip right over the surfaces of other stars. Huge stars orbiting each other. Multiple orbital systems where there's just chaos and entire objects can be kicked out of the system.
Stars gobbling up other stars, black holes eating up entire star systems, galaxies colliding with other galaxies. That's the norm.
Earth is an oasis of water and warmth. Life flourishes because of how we orbit the sun. Earth's orbit is almost circular. We stay about the same distance from the sun all year round. The temperature here is relatively constant, and Earth's orbit has been stable for the past 4.5 billion years. Without this stability, we would not exist.
To create DNA out of the oceans takes hundreds of millions, perhaps even 1 billion years. And for that stability, you need circular orbits. And so without the stability of the solar system and the Earth's orbit, there's no life on Earth.
We owe everything to Earth's orbit. We get a gentle ride. In an otherwise violent universe, we've hit the orbital jackpot. Yet chaos is never far away. Even within our solar system, there are extreme and violent orbits where life could never survive. Mercury, the closest rock to the Sun and the smallest planet in the solar system. Its orbit stretches into an oval shape. At its furthest point, Mercury is 43 million miles from the Sun. But at its closest point, it's just 28 million. This close in, it's hot.
800 degrees Fahrenheit, hotter than a baker's oven. Also, because there's very little atmosphere on Mercury, you'd choke. And because there's no air to speak of, the blood in your body would boil and it would burst your skin. You would literally explode on the surface of Mercury.
But the temperature can also fall to 300 degrees below zero, 3 times colder than the coldest place on Earth. Mercury has the most extreme temperature variations of any planet in the solar system. But it's also proof that orbits don't just loop. With each revolution around the Sun, Mercury's path shifts. Over thousands of years, the planet follows a daisy pattern. At the other end of the solar system, there's Pluto, 4 billion miles from the Sun. The further away an object is, the slower its orbit. Pluto takes 248 years to complete a single loop. And Pluto is an anomaly. Its stretched orbit is on a completely different plane from the major planets, and it creates an amazing spectacle. During most of its orbit, Pluto is a frozen block of ice and rock. But as it gets closer to the Sun, summer begins.
When Pluto warms up, the frozen ices on the surface of Pluto, these are water ices, carbon dioxide, even some carbon monoxide, maybe methane ices, they evaporate and you get a fog, and the fog gets thicker, and then you get thick clouds, and suddenly you have an actual atmosphere around Pluto that wasn't there before.
This atmosphere is thickest when Pluto is closest to the Sun. But as the planet heads back into deep space, the temperature plummets to 400 degrees below zero. It begins to snow, flakes of frozen nitrogen and methane.
As winter comes, these gases slowly begin to freeze out of the atmosphere. They may rain down in a snow-like way, but gradually they accumulate sort of a glassy, semi-transparent layer, a frozen atmosphere on the surface of Pluto.
After a bitter winter, Pluto drifts closer to the Sun, and the 248-year cycle begins again. Extreme changes like these remind us how lucky we are that Earth's orbit is stable and benign. But it's a delicate balance. The smallest change could kill us all. If Earth's orbit were closer to the Sun, we would be like our closest neighbor, Venus.
Venus is a pretty good example of what might happen to the Earth if our orbit shifted a little bit in from where we are now. Venus has this hugely thick atmosphere that traps all of the heat, and the surface is close to 900 degrees. If we moved even just a little bit closer to the Sun, we would become more like Venus.
Oceans would boil away. Our planet would become a desert. life would be destroyed. A small shift in the opposite direction, and instead of boiling, we'd freeze.
You would have snowball Earth, the Earth completely encased in ice, and that's only by moving the Earth a fraction of its distance from the Sun.
The polar ice caps would expand. Oceans would freeze. A permanent ice age would begin. The smallest shift in Earth's orbit, and we die by fire or ice. Orbits allow life to flourish, but they can also cause chaos. Orbits are even capable of destroying entire stars. Our planet's orbit makes life possible, but most orbits are violent. Space is a cosmic freeway. Nothing stands still. Everything moves around everything else, thanks to a single force, gravity.
Gravity is the universal force of attraction that spreads throughout the universe itself. It's the force that holds stars together. It's the force that binds the solar system together.
All objects have gravity, so all objects attract each other. The more mass an object has, the stronger its attraction. That's why falling apples are pulled toward Earth. In our solar system, the biggest object is the Sun. It's 700 times more massive than all the planets put together. The titanic force of the Sun's gravity pulls all the planets inward. But something stops them from falling in. The planets are in constant motion. They fly through space at incredible speed, not directly toward the Sun, but sideways, creating a tug of war between the Sun's gravity and the planet's speed. When the two balance out, the planet loops round the Sun. We call this an orbit.
An orbit is simply the motion, the path of an object around another object due to gravity. So you can have circular orbits, you can have elliptical orbits. Even if I were to take a ball and throw it in the air and catch it, very briefly, that ball is in orbit around the center of the Earth. It's just motion affected by gravity.
Imagine what would happen if the Sun had no gravity. The planet's speed would shoot them out into space. On the other hand, if the planets stopped moving, gravity would pull them into the Sun. All orbits are a balance between gravity and motion. We like to think the universe runs like clockwork, everything neat and orderly. The planets moving in cosmic harmony. But that's wrong. Orbits can be wild and unpredictable. And the more objects there are, the more unpredictable their orbits become.
Things can get complicated when you have more than two objects, all trying to orbit around each other. Then, an orbit can actually loop between one object and another. Speeds can get faster and slower. An orbit doesn't have to be just one regular path.
The universe's creativity defies the imagination. Travel out beyond Pluto, halfway to the nearest star, and you find these. Comets, chunks of ice and rock. They float in vast clouds, frozen remnants from the dawn of our solar system. Every so often, one falls towards the Sun.
They can start 1 trillion miles out and fall right above the surface of the sun. So when they're really far away, they're hardly moving at all. When they're whipping past the sun, they're moving really, really fast. And so these can be some of the most extreme orbits in the solar system. They can be so elongated, they're almost a straight line.
Comets travel at up to 1 million miles an hour. They're cosmic missiles, guided by gravity and speed. Comets show us how destructive orbits can be. Many plunge into the sun or crash into planets.
If a comet were to hit the Earth, perhaps 5-6 miles across, watch out. It would be a planet buster. It would be an object sufficient to wipe out all life as we know it on the planet.
But most comets miss. They fly in from deep space and out again on million-year orbits. But move beyond our solar system, and orbits become even more violent. Death spirals rip apart entire planets, shred stars, and even tear holes in space. The universe is unimaginably big, so there should be other Earth-like worlds out there. Scientists looking for habitable planets thought they would find orbits just like ours. They were wrong.
So now we're on HD 154088. And there it is. Looks good.
We have discovered hundreds of planets outside our solar system, but they're not like Earth at all. These are strange, alien worlds with unfamiliar orbits.
What we're finding among extrasolar planets is an incredible diversity of these orbital shapes and sizes. Some of the orbits are extremely tight around their host star, the planet going around in just hours or days. So we're seeing interactions and shapes and sizes of orbits that are like nothing we ever imagined.
Some worlds are so hostile, life as we know it would be impossible. This is WASP 18b. It's a hot Jupiter, a class of huge planets that closely orbit their stars. WASP 18b is 50 times closer to its star than we are to the Sun. It's so close, it orbits in less than 1 day.
If you had said, what's the weirdest, least likely orbit you could possibly imagine? I would have said, take something like Jupiter and plop it down right next to a star, 5 million miles away. And it turns out I would be totally wrong. That is an extremely common thing that we see in the universe. In fact, most of the planets that we're discovering around other stars appear to be in orbits like that.
This cosmic duel produces incredibly powerful physical effects. WASP 18b burns at 4,000 degrees. Thermal hurricanes blast across its surface, and both star and planet are distorted by vast gravitational forces, the same forces that cause the tides on Earth.
Everybody is familiar with the idea of tides. In the course of a day, the level of the oceans get higher and then lower. Well, that's from the influence of the sun and the moon, from the influence of orbits, things that are going around us or that we're going around. If you bring things closer together, tides become more extreme. Planets can actually get pulled into different shapes.
WASP 18b was formed in a cold region of space, far away from its star. Over millions of years, it spiraled into its present position. It's locked in a gravitational battle that can only end one way. Less than 1 million years from now, it will be consumed by fire.
The key conclusion you have to draw is when you see the universe today, it won't be that way tomorrow, and it won't be that way the week or the millennium or a billion years later because of gravity.
Our search for Earth-like planets reveals a destructive universe, from the deadly, missile-like orbits of comets to the searing paths of hot Jupiters. There are even planets that don't seem to orbit anything at all. Scientists have recently detected tiny fluctuations in the light from distant stars. The only explanation? A massive object between us and them. These rogue planets don't orbit a parent star. They are planetary orphans, all alone in space.
Planets, by definition, go around stars. So, boy, were we shocked to find rogue planets. Rogue planets are a contradiction in terms. Planets without a mother star.
Scientists think every rogue planet did once orbit a star, until gravity hurled them away. New solar systems are chaotic places. Planets tug on each other and dramatically change course. Some planets even spiral out to wander the galaxy alone.
The presence of rogue planets shows us that gravity is not just this attractive force which binds the solar system together, it can also fling entire planets into outer space.
A recent sky survey suggests our galaxy contains more rogue planets than stars. We've discovered orbits we didn't even know were possible. Gravity and motion keep our universe in constant turmoil. Vast orbiting suns cannibalize each other. Violent vortexes distort space itself. And powerful forces flick a star like a spinning top. Gravity causes chaos on an epic scale, hurling planets to their destruction or firing them off into space. But the cosmic roller coaster gets even more extreme. Orbits become so violent, they rip chunks out of stars. This is HM Cancri, a binary star system 16,000 light-years from Earth. They're white dwarfs, small but incredibly dense. 1 teaspoon of white dwarf matter can weigh 5 tons. The stars are just 50,000 miles apart, 5 times closer than we are to the Moon. They orbit at more than 1 million miles an hour.
We have 2 white dwarfs an infinitesimal distance apart, rotating around each other in 5.5 minutes. This is a world's record for an astronomical body in space.
The forces are immense. Gravity rips superheated gas out of one star and slams it into the other. Scientists believe this orbit is so violent, it warps the fabric of space itself. In the process, the stars lose energy, falling even closer. Eventually, they'll collide, creating a supernova.
A supernova is one of the most violent, energetic events in the universe today. You are blowing up a star. There's no way to describe that kind of energy.
Some supernovae are so powerful, they are second only to the Big Bang itself for energy and sheer power. They are so magnificent, they can outshine an entire galaxy of 200 billion stars.
Supernovas can create one of the weirdest objects in the universe, a pulsar. Pulsars are intensely magnetic stars. They fire out beams of electromagnetic radiation that sweep across space.
There are few things in the universe more dramatic than a pulsar. Imagine a ball about 10 miles across, rotating hundreds of times a second. With a density that's almost unimaginable, 1 cubic centimeter of this material would have as much mass as Mount Everest.
You would feel a gravity that is millions of times what you're feeling sitting on the surface of the Earth. You wouldn't just be crushed flat by this. You would be crushed into a paste that is only a few atoms thick.
Anything that orbits a pulsar too closely risks being torn to shreds. This is the Black Widow pulsar. It rips through our galaxy at 600,000 miles an hour. The shock wave is so vast, our telescopes can detect it 5,000 light years away. Traveling alongside it, a brown dwarf, bigger than a planet, smaller than a star. The pair are locked in an orbital dance of death.
The Black Widow, in some sense, is like a vampire, sucking the lifeblood from this brown dwarf star, eating away at its hydrogen and helium fuel.
Radiation blasts the brown dwarf's gases into space. A pulsar just 10 miles wide is destroying an object bigger than Jupiter. Eventually, the brown dwarf will evaporate. A single pulsar has immense destructive power. But 2 pulsars together can change the shape of the universe. This is the only known double pulsar system in our galaxy. Orbiting at 700,000 miles an hour, their speed and mass make them spin chaotically.
It's incredible to think of the enormous forces gravitationally that these 2 stars exert on each other, causing the whole geometry, the architecture of the system to change and spin around like a top on the table.
The gravity of the heavier pulsar makes the smaller one wobble erratically. It whips around so violently that the whole star almost tips over, just like a spinning top. It can't last forever. 85 million years from now, the 2 pulsars will merge to form a vast gravitational abyss. The universe's ultimate monster, a black hole. A black hole, the most extreme object in the universe. At its center, the laws of physics break down. Time comes to an end. Gravity is infinite.
A black hole is a bottomless pit of gravity caused by the death of a star. There is nothing in the universe more mysterious than how black holes work.
If you want to talk about extreme orbits and extreme gravity, you're talking black holes. That is at the top of the list. Nothing has stronger gravity than a black hole. It is the mass of something like the sun or more, compressed down into a ball that's only a couple of miles across.
50 years ago, black holes were dismissed as science fiction, but not anymore.
Now we see them at the center of galaxies, wandering through outer space. Black holes, we now know, are central to the evolution of the universe.
We now think there may be 100 million black holes in our galaxy alone. an encounter with any of them leads to oblivion. This is one of the largest and hottest stars in the universe. It's 20 times more massive than our Sun and 10 times hotter. Stars like this never live long, but this one is locked in a diabolic waltz, trapped in the grip of a black hole. The gravity here is so powerful, the star orbits at 500,000 miles an hour. The black hole sucks the star's outer layers into a vast, swirling disk. A disk so hot, it blasts out X-rays 1,000,000 times more powerful than our Sun.
This configuration, a star orbiting around a black hole, is extreme and it's unstable. First of all, the black hole is eating away at the atmosphere of its companion star, but the star itself is unstable. It will one day undergo a supernova and perhaps leave a black hole in its wake. And then we'll have two black holes rotating around each other, one of the rarest sights in the universe.
Eventually, these black holes will merge to create a new, larger monster, and the cycle of destruction will continue. But this black hole is small. Other black holes take violence to a whole new level. In 2011, astronomers witnessed one of the biggest explosions ever recorded. A flash of radiation brighter than 100 billion suns. A gamma ray burst. It was a spectacular event. The burst came from a supermassive black hole at the center of a distant galaxy. It had been dormant, but something had shocked it back to life.
If you pass by the event horizon, an imaginary sphere surrounding the black hole, that's the point of no return. It's like the ultimate Roche motel. Everything checks in, nothing checks out.
Several stars were orbiting the black hole at a safe distance. Then one of them got too close. The sleeping giant suddenly awoke. Immense gravitational forces stretched the star to its breaking point until finally it was torn apart. Debris swirled round the black hole, heated to millions of degrees. Two giant jets of gamma rays blasted into space at the speed of light.
A black hole has torn a star apart, swallowed up half of the material of the star, and ejected the other half in an event that is among the most violent things we have ever seen in the history of astronomy.
The event was so violent, we saw it from Earth 3 billion light years away. Black holes can suck in planets and rip apart stars. But gravity doesn't always pull things in.
Any high school student knows that gravity sucks. It pulls, it never pushes. But it's actually more complicated. That's true when you just have two objects. But the minute you have more than two objects, strange things can happen, and gravity can actually push you away.
You can get very close to a body, but if you come in at just the right angle and just the right speed, instead of colliding together, one object can slingshot the other one away.
Recently, scientists discovered stars hurtling away from our galaxy at incredible speed. Normal stars don't do this. So what could accelerate a star to hypervelocity? The answer was a surprise.
You can only eject stars at these very, very high velocities, so close to 700, 800, 1,000 kilometers a second. You could only eject these with interactions with the supermassive black hole.
Each hypervelocity star was originally one of a pair of stars orbiting a supermassive black hole. When they got too close, gravity pulled them apart. The black hole catapulted one star out of the galaxy at 2 million miles an hour. Eventually, the other was sucked in and destroyed.
The interesting thing here is that you can get a complete redistribution of stars. So you have stars that are in the center of the galaxy and suddenly they're ejected out into intergalactic space.
And it's out here in deep space that orbits are at their most powerful, smashing entire galaxies together to create the structure of the universe itself. Across the universe, extreme gravity is a force of destruction. The orbits of planets and stars can be chaotic, unpredictable, and violent. But on a truly cosmic scale, gravity is no longer just a destroyer. It also creates new worlds. These are galaxies, giant spinning clusters of stars, gas, and dust, 100,000 light years across. Galaxies orbit each other in the same way planets orbit stars. Gravity pulls them together. Their speed keeps them apart. But ultimately, gravity always wins. Entire galaxies smash together.
One of the most spectacular events in the universe is when galaxies collide. You're talking about hundreds of billions of stars, 100,000 light years across. Two of these things slamming into each other.
Collisions between orbiting galaxies take place over millions of years. Gravity slowly pulls them together.
And you get these two galaxies that merge like two fluids mixing together, and you get long tidal tails as they pass through each other, but then gravity brings them back together again, and in the end, you get a full-fledged, more mature, larger galaxy than you had originally.
On this intergalactic scale, gravity and motion are no longer destructive forces. Now, they trigger the creation of life itself.
You would think a galactic collision would be incredibly destructive, and in one sense it is, but in another sense it's a very creative force.
Colliding galaxies smash vast gas clouds together. Huge shock waves rip through them, squeezing the gas. Then something amazing happens, the birth of countless stars.
It's incredible to think about two galaxies that gravitationally attract each other and collide. What could be more destructive? But in fact, there's a power of construction in such mergers, because as two galaxies come together, the gases are compressed, and sometimes the gases are compressed so much that you get the birth of stars and the associated planets around those stars. And so in the titanic collision between two galaxies, you can get the birth of stars and planets and perhaps eventually life on those planets.
Sometimes these collisions trigger a chain reaction. Two spiral galaxies in mid-collision, creating stars and planets. But this time, there's a difference. Some of these new stars are massive, unstable, and short-lived. They explode. Each explosion blasts out new shock waves and triggers the birth of even more stars. Astronomers call this a starburst. It's the ultimate example of gravity's creative power.
A starburst galaxy is one that is creating stars at a much higher rate than we usually see in normal galaxies. And so it's amazing that you can have such a beautiful creative process coming out of something so violent and destructive.
Gravity and motion, the two forces that give birth to every new star, also weave together the fabric of the universe itself. Our cosmos is not random. It has structure. The universe is a vast three-dimensional tapestry. Each of these threads and filaments contains billions of galaxies. It's the scaffolding that holds everything together, the cosmic web.
When we think about scaffolding of a building, it's just sitting there static. But in fact, this scaffolding is quite dynamic and quite amazing because all of the constituents are moving around at very high speeds, crashing into one another. Galaxies, stars, black holes, supernovae, all in this tremendous cosmic dance.
The cosmic web is incomprehensibly vast. Each thread is full of motion. Galaxies form, orbit, and collide, countless billions in a constant stream. Every filament is a galactic freeway with an endless flow of traffic. Each point of light a galaxy. It's rush hour 24/7, and sometimes there's gridlock. Every billion light years, several filaments join to form a knot. Whole clusters collide to form some of the largest structures we know of, superclusters. This is one of them, Able 2744. 5 orbiting galaxy clusters crashed together in the single biggest cosmic pileup ever discovered. Gradually, the 5 clusters merged and fused to form a single giant supercluster 6 million light years across. The incredible power of orbits can literally tie the universe in knots.
Structures in the universe have evolved over billions of years through their orbits and their mutual gravitational attraction, and they've built up into larger and larger structures. And it's all thanks to these same attractive forces that bring them together, but can also tear them apart.
Again and again, we discover orbits dominating the cosmos.
The atom is the basic unit of chemistry. In the same way, the orbit is the basic unit of the universe itself. If you understand all possible orbits, you understand the dynamics driving the universe.
Orbits have created a cosmos full of richness and complexity.
Orbits are changeable, they're chaotic. Things that we never thought were possible are in fact possible.
From the smallest scale to the largest scale, it's the gravitational interactions and collisions that actually make our universe the beautiful place that it is.
And behind it all is a curious paradox. A dramatic streak of light across the sky, a passing comet, is an astonishing sight.
They're beautiful, these fuzzy glowing balls with the tail coming off. It's really something. You just don't get to see an object like that very often.
Comets are extraordinary. If you get to see a comet for the very first time, it'll stick with you forever.
The journey of a comet as it sails through the solar system is the most fantastic of all astronomical objects.
It loops in toward the sun from the depths of space, an odyssey that can last millions of years. Many pass by the Earth so often, they're almost like old friends. Every comet is a frozen mass of rock and ice several miles across. But all we see is a glowing ball of light and a long, sweeping tail. Yet comets are more than cosmic fireworks. They could help unlock some of the deepest mysteries in science.
We're trying to figure out as scientists where we came from, and that means everything from the beginning of the universe to the beginning of the solar system to how life started. Comets really fit into that. They really give us clues about how the solar system formed. If we can't understand comets, we don't understand how we got here.
Comets may even be the source of life itself.
We may owe our existence to the fact that comets billions of years ago came to Earth and brought the necessary ingredients for life.
They can also cause enormous destruction. Comets could kill us all.
If a comet were to hit the Earth, watch out. It would be a planet buster. It would be an object sufficient to wipe out all life as we know it on the planet.
Learn about comets, and just maybe we will learn how to survive them and begin to understand how the universe works.
When we study them, we're learning what the solar system was like when it was first forming, and we can learn about what other solar systems were like as well. And hopefully that will teach us a tremendous amount about how stars form and how planets form, and how comets themselves were originally formed.
Comets date back to the birth of our solar system 4.5 billion years ago. They were made by the same force that created the solar system, gravity. It began in a maelstrom of chaos. A giant cloud of gas and dust collapsed to form a whirling disk. Close to the sun, it was burning hot. But further out, it was cool enough for gas clouds to condense and freeze. Ice crystals fused with grains of dust. They slowly pulled together into larger and larger masses.
Over time, these sort of snowballed, like a snowball rolling downhill, picking up more and more and more material.
Eventually, they formed gas giants like Jupiter and Saturn. But not all the debris in the disk turned into planets. Trillions of lumps of dirty ice were left behind. The comets.
You could almost think of comets as sort of the frozen leftovers of the formation of the solar system.
They are almost unchanged to this day.
They're pristine time capsules, and if you could crack one open and see what was inside, you could literally see what the solar system was first made out of. That's remarkable.
But the comets did not stay put. Several 100 million years later, the solar system plunged into turmoil once again. Encounters with debris pulled the gas giants out of position. The giants' immense gravity then hurled comets in every direction, flinging trillions of tons of material from the dawn of the solar system into the cold outer reaches of space. Some comets settled in a region 4,000 million miles from the sun. the Kuiper belt. But most were tossed even farther out to form a giant sphere around the entire solar system. We call it the Oort cloud.
This is a region of our solar system that's farthest away from the sun. The sun is just a tiny little dot, one of many stars. And the whole area of space around you is virtually empty. There's nothing there, very little. And just occasionally you'll find the odd comet floating out there in deep freeze, cold, dark, and very much alone.
In this remote ice cloud, there are more than 1 trillion comets. They can take millions of years to orbit the sun. But they don't always stay here. The orbit of every comet is a delicate gravitational balance. The smallest nudge can tip the scale.
Most comets spend their entire lifespan billions of miles from the sun, motionless, inert, simply waiting for something to happen. But then, perhaps a random collision takes place. Perhaps a passing star nudges it, and then the gravitational force of the sun inevitably pulls it toward the inner solar system.
Gravity, the force that created the comets, then flung them to the edge of the solar system, now pulls them back in. Our comet begins its epic odyssey to spread life or death across the solar system. More than 1 trillion comets circle the sun at the frozen edges of our solar system. But many do not stay here. The smallest gravitational disruption can knock them out of their orbit.
It could be a nearby star going by. It could be us going through a denser part of the galaxy. Anything that just gives a little gravitational hit to a comet can cause it to fall in towards us.
Our comet has been disturbed. Now the sun's immense gravity takes over.
You can think of the gravity of our solar system sort of like being a hillside. At the bottom, there's the sun, and comets are way at the top of that hill. When they get dislodged, there's only one way for them to go. They have to fall down in towards the sun.
Our comet accelerates towards the sun, but its path is far from straight. Gravity from the planets can throw comets off course or out of the solar system completely. If they escape these obstacles, comets continue their journey toward the sun. Now they begin one of the most remarkable transformations known to science.
A chrysalis to a butterfly. They become the most spectacular things the universe has to offer.
As it passes Jupiter, our comet begins to change.
As it starts to move a little bit faster and starts getting closer and closer to the sun, and it starts feeling the heat of the sun, that's when things really start to change.
"500 million miles from the sun, heat brings our comet to life. Frozen gases start to vaporize. Grains of ice and dust rise from the surface.
As the comet continues to approach the sun and gets warmer, more and more gas is released. The comet becomes a fuzzy ball. There's a solid part in there, but it's surrounded by a much larger sort of cloud of material.
This cloud of dust and gas forms an atmosphere or coma around the comet. And it also creates the comet's huge tail. It's all driven by the sun, and it's not over yet.
There's something called the solar wind. It's actually a huge wave of charged particles originating from the sun. This fills our solar system, and as a comet begins to move further and further in towards the sun, the solar wind gets stronger.
Like a cosmic hurricane, the solar wind blasts gas molecules from our comet out into space. they form a second giant tail.
The solid part of the comet might only be a few miles across, and the fuzzy part might be a few thousand or tens of thousands of miles across. The tail that gets swept back as that material is blown off by the solar wind can be millions or tens of millions of miles long.
Our comet hurtles through space at 50,000 miles an hour. It's about to enter the most violent phase of its journey. 200 million miles from the sun, water ice begins to vaporize.
The ground would start to shift and quake, and as the material beneath my feet is literally thawing, we'd have great big jets of carbon dioxide and water ice starting to come out. And that would not be a very good place to be standing.
The surface cracks open. Gases explode. Debris fires in all directions. The force of these eruptions makes the comet tumble erratically.
Every jet that turns on is literally like a little jet engine attached to the comet.
Like a dragster on a racetrack, our comet explodes to life. Incredible speed, irresistible energy, and a vast plume of debris. Our comet transforms into a cosmic hot rod, but speed and energy are a volatile mix. Our comet could blow apart at any moment. The cloud around our comet is now bigger than Jupiter. Its tail stretches for 100 million miles. An object 4.5 billion years old emerges from the dark.
Every arrival of a new comet is like a gift from the universe. We've never seen this little bit of the solar system before. This little building block, this little baby picture, it's completely new to us.
It's a chance to study the origin of our solar system. And what we're learning is a revelation. Comets are far more hostile and alien than we imagined. With modern telescopes, we can study comets in more detail than ever before. But to really understand them, we need to get close to the very heart of a comet, its nucleus.
One of the holy grails of comet science is to really understand what is in a comet's nucleus, what is actually on the surface, what is the chemical composition, what are the characteristics of the rocks and the materials, the volatiles that are on that surface.
The nucleus is the fundamental building block of the solar system that we as scientists really want to investigate. That's where the mysteries really are.
There have been more than a dozen missions to comets in the past 3 decades. Every one of them has been a revelation.
We've learned about the chemistry of them. We've learned about the physical interaction they have with the sun. We've learned about their physical surface, their terrain, and how they're different even if you were to go from one spot on a comet to another. So we're really learning that these things are worlds unto themselves.
Scientists thought comets were white, like a snowball. That changed in 1986. When the Giotto space probe beamed back these images of Halley's Comet.
For the first time in history, we had a snapshot of the very center of that comet that entered human history on many occasions, and we found a cold, dead world. We found an object shaped like a peanut.
Halley was no snowball. A thick layer of black dust covered its surface. There were pits and hills, and Halley was 9 miles long. Far bigger than anyone expected. Scientists thought that all comets were the same. They were wrong. In 2004, the Stardust probe flew into the tail of Comet Wild 2 and captured thousands of tiny dust particles.
When Stardust brought those samples back on Earth, we realized that, in fact, every comet is a unique object. Just like every planet is different, it looks like every comet is different. It has its own history to tell. Different materials went into its formation, different heat sources were injected into its interior, different chemical processes and geologic processes occurred. Each one is a unique world waiting to be explored.
Some comets are truly strange. These are real images of Hartley 2, a comet so weird, it snows.
It's so strange. We were able to see that there are golf ball-sized chunks of dry ice that are following the comet around up to 1 million miles away from the nucleus. This thing is just making a big mess.
Hartley 2 is just amazing. It looked like you were in the middle of a snow globe and you shook it up and there are all these little things, kind of like flies buzzing around food, just kind of floating out there. It's just not right.
Hartley 2 is a hyperactive comet. It tumbles faster and spits out more debris than most others its size. Comets are alien worlds. On Comet Tempel 1, there are smooth plateaus, craters and cliffs 60 feet high. Layers of rock lie on top of each other like a stack of pancakes. Each comet seems to have its own unique history. Tempel 1 gave scientists their biggest breakthrough. In 2005, the Deep Impact Space Probe slammed a projectile into its surface. The explosion dug out a crater 150 yards across.
Talk about a spectacular 4th of July. I mean, can you imagine anything better? We actually blew a hole in a comet. I mean, that's got to be one of the more amazing things that NASA has ever done.
The material the impact ejected allowed us to see inside a comet's nucleus for the first time.
It was completely unexpected. We found things like rubies and peridot, gemstones, tiny little things inside the comet. And we found all kinds of organic molecules, the very sorts of things we're made of.
Scientists now believe that comets play a critical role in our universe.
Where do the ingredients of life come from? Where were they all mixed together? Where did all this liquid water come from? Comets could hold the key to understanding the nature of life itself.
But opportunities to study them up close are rare. Our comet is now moving at incredible speed toward a place where no spacecraft could ever survive: the Sun. 4 billion years ago, gravity hurled comets to the edges of our solar system. The same force can pull them back in. Our comet passes Earth and enters the most violent stage of its journey. It rockets toward the Sun at 100,000 miles per hour.
The surface of the comet is now sizzling with activity. Blistering temperatures are being created. Enormous geysers of ice crystals and gas being shot off the surface.
Jets are erupting all over the place. It's tumbling, the rotational state is changing, and the very surface is kind of cracking up underneath our feet.
Inside the comet, pockets of gas explode and fling huge rocks into space.
It's losing mass, it's shrinking. And as we get closer and closer to the Sun and more of the volatiles are starting to come off of its surface, this can actually change the rotational state of the comet. It can make it tumble, it can actually even push it in its orbit. It can actually change the orbit of the comet.
Comets can shed 50 tons of ice and gas every second. Enormous pressures build up inside the nucleus.
It could become unstable. It could even break apart into pieces at any time.
As comets reach their closest point to the sun, their existence is on a knife edge. Many will not survive.
We've been able to actually see images of comets just getting swallowed up by the sun. And you can actually see them just pelting in there, and the whole body, whether it's a mile across or 10 miles across, just gets completely and utterly destroyed.
A solar observatory recorded these extraordinary images. They show small comets called sun grazers diving towards the sun. Here they're exposed to immense gravity and torched by the ferocious heat of the sun. Many are vaporized. Even in deep space, vast explosions can tear comets apart. In 2007, Comet Holmes was heading away from the sun when something extraordinary happened. In less than a day, it grew 500,000 times brighter. The cloud around it ballooned into space.
It's actually relatively common for a coma, the fuzzy part around a comet, to expand large enough to be bigger than Jupiter, 100,000 miles across. But that can take days and weeks and months to build up. To have a single event, something that happened, boom, all at once, some catastrophe, to create this shell around Comet Holmes that could be bigger than Jupiter is amazing to me.
We had never seen something like this before. In fact, the coma of the comet was actually larger than the sun itself. Briefly, it was the largest object in the entire solar system, something that was unprecedented.
Without warning, Comet Holmes blew apart. The largest cometary explosion ever recorded. The debris stretched for 1,000,000 miles. What caused it is still unclear.
One theory is that perhaps Comet Holmes slammed into an asteroid of some sort, creating this gigantic mega flare in outer space. Another possibility is perhaps the comet was unstable, and perhaps there was an explosion caused by expanding gas and ripped the entire comet apart. At the present time, we simply don't know.
The life of all comets hangs by a thread. Our comet survives its encounter with the sun, but it's paid a price.
Its geography has been totally rearranged. Huge chunks, mountaintops worth of rock have disappeared. An object which could be perhaps 10, 20 miles across has lost literally hundreds, perhaps thousands of tons of rock and ice on its journey.
As our comet leaves the sun behind, activity on its surface subsides.
On its outward journey, a comet gradually begins to shut down. It becomes cooler, less active, the jets begin to turn off, the coma begins to blow away, and you're left with this little ball of ice and dirt.
It returns to the depths of space, dormant once again. But the sun is just one of many challenges. Comets must also survive the gravitational pull of the planets.
Our gravity is way too small to have any effect on this comet, but Jupiter is a very large planet. It has 300 times the mass of the Earth. If the comet passes within even a few million miles of Jupiter, that can change its orbit.
The consequences can be catastrophic. In 1994, a comet called Shoemaker-Levy 9 flew too close to Jupiter. Scientists watched the planet's immense gravity tear it apart. The remains headed straight toward Jupiter.
Many people thought that the impacts wouldn't do anything to Jupiter, that Jupiter would just sort of swallow it up without a burp. And that's not what happened at all.
21 comet fragments smashed into Jupiter's atmosphere. Each impact released more energy than all the world's nuclear arsenals combined.
Comet Shoemaker-Levy 9 was not a particularly massive comet, and it wasn't even a very dense one. It actually had the consistency of cotton candy. You could have pulled bits of it apart with your fingers. But this rather tenuous little icy creature created unimaginable destruction.
The impacts hurled plumes of debris thousands of miles high and scarred Jupiter's atmosphere with dark lesions. The event rocked the scientific community.
To actually see it for ourselves, to actually see the immense destructive power by an object that's really not that much bigger than a hill, was really pretty terrifying. Even though we knew the math, to see it for ourselves was amazing.
The Shoemaker-Levy 9 impact really woke astronomers up to the fact that impacts can happen now, and they can happen here.
If a comet just a few miles across hit our planet, the result would be catastrophic. Tidal waves would devastate the land. Debris would rain from the sky. Life as we know it would end. Yet comet impacts can also be a creative force. They could even trigger the birth of life itself. Across the universe, comets cause massive destruction.
They could be moving 50 or more times faster than a rifle bullet. And we're talking about something the size of a mountain. So the amount of energy that this thing would release upon impact is devastating.
But they're not always destructive. They have another side. Scientists believe they can shape entire worlds. This is Titan, the largest of Saturn's moons. It's the only moon in our solar system with a thick atmosphere. Rivers and lakes of liquid methane cover its surface. Titan was transformed by comets. Radar images reveal a moon shaped by a blizzard of comets that rained down over millions of years. Each comet vaporized when it hit, releasing gases from inside its nucleus. Gradually, they built up a rich, organic atmosphere and this strange liquid landscape. Comets turned a space rock into an Earth-like world.
Comets, in some sense, are the ultimate engineers of the solar system. Cometary impacts could give us the chemicals which give us the atmosphere, not just of Titan, but even perhaps the Earth itself.
So if comets have the power to reshape entire worlds, what part did they play in the history of our own planet? To find out, we need to get closer to a comet than ever before. We need to land on one. In March 2004, the Rosetta mission launched.
The Rosetta mission is named after the Rosetta Stone because just like the stone gave linguists the keys to the ancient language, we're hoping that the comet will give us the keys to understanding the ancient solar system.
November 11th, 2014 will be a landmark in space exploration. For the very first time, a spacecraft will touch down on the surface of a comet.
Previous missions to comets were basically flybys, and they basically give us tantalizing evidence that there was a greater mystery yet to be solved. Now we're going to land on a comet. We're going to be up close and dirty with a live comet streaming through outer space, and this is unprecedented.
Rosetta is around the size of a car. It's flying through space at 20,000 miles per hour. It's heading for this. A comet with a nucleus 3 miles wide, orbiting the sun every 6.5 years. A robotic lander will drop down to the surface, beginning the most detailed study of a comet ever attempted.
It's going to look at what the surface looks like. It's going to take samples. It's going to look at the terrain. It's going to be able to actually probe inside the comet and see what it's made of and how it's put together. We're hopefully going to learn more from this mission about one comet than we have about just everything we've known about comets for centuries.
Rosetta should answer some very simple questions.
Is it porous? Is it like a sponge? Is it like a bunch of tubes? Is it like a snowflake, you know, with this sort of fairy castle structure? These things will help us to understand how the heat flows within and maybe what causes certain portions of it to become a jet and other portions not.
But this is just the beginning. For an entire year, Rosetta will study the comet on its epic journey round the sun. Using technology so advanced, it mimics the 5 human senses.
We've got instruments that can see. We've got a kind of an ultrasound experiment, instruments that are the equivalent of your hands. So we'd like to understand everything possible about this comet's journey around the sun from when it's quiet to when it's at its most active.
But we'll have to get there first. Just to reach the comet, scientists must overcome enormous technical challenges. Rosetta must hit a target just 3 miles wide, traveling at 34,000 miles per hour. Landing on it will be even harder. Comets have very little gravity.
There's not anything that you know is going to pull you down to the surface. And there's no atmosphere, so you can't unfurl a parachute and just sail down until you touch down. You've got to figure out a way to get your lander to actually reside and rest on the surface.
Technicians have an ingenious solution. The lander is equipped with shock absorbers and a harpoon.
When it makes contact with the surface, at the same time, the harpoon will be released down into the substrate, and it will have prongs that will open that will prevent it from coming back up.
Rosetta will attempt to solve some of science's deepest mysteries.
We would very much like to know, why is it that Earth has liquid water, and so much of it, compared to any place else that we've ever seen? So how is it that the water got here? Now, there is a theory that says that comets delivered the water to the Earth long ago. But the question is, can we actually prove it?
To find out, the lander will collect water molecules to compare with water from Earth. But scientists hope to go even further. We're on the brink of making an extraordinary discovery. We may find proof that life itself has an extraterrestrial origin, that it was brought to Earth by comets. Life has existed on our planet for at least 3.5 billion years. But we still don't understand its beginnings. We used to think life originated on Earth itself, that volcanic gases and water vapor formed oceans and an atmosphere. Lightning added the creative spark for early life to begin. Now we think that's wrong, and the evidence is in space. In 1997, Comet Hale-Bopp appeared, one of the biggest and brightest comets ever recorded. Scientists found it was packed with water, gases, and carbon, the basic ingredients for life. That discovery raised profound questions.
We're all used to the idea that life originated here on Earth, and it probably did, at least complex life. But where did the building blocks come from? Where did the water that makes up our body, the organic molecules that make up the very essence of life, they actually may not have been intrinsically part of the Earth to begin with. They came from somewhere else.
Hale-Bopp suggested that the raw materials for life might have an extraterrestrial origin. Since then, scientists have found further evidence. Astrobiologist Dante Loretta discovered that dust from Comet Wilt 2 contained minerals that could only form in heat and liquid water.
We had the sulfide minerals, we had iron oxides, we had carbonate minerals, which are the same kind of materials that marine organisms use to build their shells, unlike anything we thought was possible to be formed in the early solar system.
Scientists have even found that Comet Wilt 2 contains amino acids.
That's incredibly exciting because amino acids are the building blocks of proteins, and proteins are essential biomolecules for all life on Earth.
These discoveries have transformed our understanding of comets. Many scientists now believe they're more than just frozen time capsules. Perhaps they play a central role in the history of our planet.
We have learned from study of a single comet and the results of the Stardust mission that they are complex chemical laboratories where the ingredients of life could form. These materials likely did not arise naturally on the surface of the Earth from processes on our planet. Instead, they had to be delivered by these messengers from the outer solar system.
The idea that we may owe our existence to comet impacts is astounding, but not everyone is convinced.
There's pretty good circumstantial evidence that a comet might have been important to life. But we don't really have, if we're CSI, if we're the comet science investigators trying to prove it, we haven't got the proof lined up yet. It's quite possible that what we have out there has nothing to do with life as we know it on Earth.
Scientists hope the Rosetta mission will resolve the issue.
If we can establish a correlation between amino acids on comets and the amino acids we have on Earth, life on Earth, that would be one of the most significant findings in science.
The story of life on Earth began 4.5 billion years ago. When our planet formed, it was a barren, hostile world. 700 million years later, the solar system plunged into turmoil. Gravity ripped comets from their orbits and hurled them in all directions, many into the inner solar system. They rained down on the early Earth for 300 million years. They released gases and organic material, creating an atmosphere and the oceans. Finally, life could begin. It's a dramatic story. But is it true?
Only time is going to tell, if we keep studying these mysterious objects, whether or not we can really pin down exactly the mechanisms and find out how it all got started.
In 100 years' time, hopefully we'll look back and say, wouldn't it be cool to have been living at that time, to be a witness, to be one of the first to make these incredible discoveries?
In the meantime, the search for proof continues.
I can't say for sure if comets brought all of these raw ingredients to the Earth and that we evolved from these materials, but it's certainly possible, and it's absolutely poetic to think that we came from out there.